Hello everybody. If we are talking about something rotating, there are two different ideas of speed that might be relevant. One is called rotational speed, and the idea there is it measures how fast your angle is changing. Different than that is linear speed, which would be your speed in feet per second if you were actually walking along the perimeter of the circle. If you're thinking, wait, why are we calling it linear speed if we're not walking in a line? That's a great thought. We are walking along part of a circle, but we still call it linear speed. Sometimes it's called tangential speed. Okay, so let's look at how these things are different. Let's say that at time 0, I want to have an angle pointed this direction at 0. And then 3 seconds later, I want the angle to be pi over 2, or straight up. What's my rotational speed? Well, I can just say how much did the angle change in how much time. So here it went from 0 to pi over 2, so that's a change of pi over 2 radians. And it took 3 seconds. So simplifying that, I've got pi over 6 radians per second. Okay, I can now use that to create a vector that actually rotates at that speed. So the form of a rotating vector looks like this. If I wanted to make it larger, I could add a scale factor on the outside, which would stretch it by 3. But that doesn't affect the rotational speed. That just affects the length of the vector. So the rotational speed would be a scale factor on the inside here. And we can think about why that makes sense in just a second. But that would be a vector that rotates at the speed I want, which would take it from angle 0 at time 0 up to angle pi over 2 at time 3. A really easy way to check those things, by the way, is just plug in time 0. If I plug in 0 for t, I'm going to get 0 right where the angle is. If I plug in 3 for t, I have 6 dividing 3, which would simplify as pi over 2. So you can always imagine plugging in the value you want. Okay, so why does putting a multiplier there affect the speed of rotation? Well, let's go back and think about how we calculated the rotational speed. We said pi over 2 divided by 3. So you can imagine this pi over 2 angle, but let's say we've divided it into 3 equally sized parts. So I've got one part here, one part there, one part here. Each of those parts has a size of pi over 6. And you can see that if I add 3 pi over 6's together, that gets me all the way back up to pi over 2. Okay, so now let's imagine time here. Let's imagine t going from 0 to 1 to 2. When t is 0, that means this whole expression simplifies to 0, so that corresponds to this angle. If t becomes 1, now I've got an angle of pi over 6, so that corresponds to having rotated through that much. If time is 2, now I have 2 of the pi over 6's, so that corresponds to having gone through that much. And then when time is 3, that corresponds to all 3. So in other words, every single time t goes up by 1, my angle is also increasing by pi over 6. And that's why it has the meaning of rotational rate. It's because it's telling me how much my angle changes every single time t increases. Okay, so how is linear speed different? So remember, linear speed is the total distance that somebody travels divided by how long it took. This one depends on the size of the circle. If I imagine something rotating from here to there in 3 seconds, that's going to be true no matter how big the circle is, because it's about how fast the angle is changing. But if I'm imagining a person walking, if it takes this person 3 seconds to walk from here to here, they are walking a lot slower than this person has to walk. Because if this person takes 3 seconds to walk from here to here, they have a lot further to go, so they're going to have to walk a lot faster. So that's the idea of linear speed. So let's calculate the linear speed for, let's do both people. So let's say this is radius 1, let's say this is radius 3. I know this is not to scale, just, be cool with the labels. So if I want to know how far did this person walking around a radius 1 circle go, well, let's see, that's a quarter of a circle. How far is the circle all the way around? Well, that must be the circumference. So the circumference of the circle is 2 pi r. In our case, the radius is just 1. So that means it's 2 pi all the way around. Okay, how far is it to go a quarter of that? Must be 2 pi over 4, or pi over 2. you'll notice that that's exactly the same as the angle measure. And that's because that's how radians were defined. Radians are defined so that the measure of the angle is the same as the length of the arc of the circle when the circle is radius 1. Okay, so let's go back to linear speed. So I know it took me 3 seconds to walk that far. That distance is pi over 2. So pi over 2 divided by 3 also gives me pi over 6 feet per second. So in the case of a radius 1 circle, my linear speed was the same number as my rotational speed, but the units are different. The units for linear speed would be feet per second. But now let's look at this case when the radius is a little bit bigger. So if I've got radius 3, let's do that here. So 2 pi times 3 gives me a circumference of 6 pi. So a quarter of that circumference is 6 pi over 4, which simplifies as 3 pi over 2. So we're still imagining walking that full 3 pi over 2 distance in 3 seconds. So here my linear speed, which I'll just call speed, if I walk 3 pi over 2 feet in 3 seconds, let's see, the 3 divides the 3, and that gives me pi over 2 feet per second. And that's different than the rotational rate, which is still pi over 6 radians per second. So I think all of this stuff is actually pretty simple if you just keep in mind the definitions. Think, okay, do I want to know rotational speed? How far did my angle change in a certain amount of time? Do I want to know linear speed? Think about 2 different times and ask, how far did you go? How long did it take? And you can always make sense of things by going back to a couple of concrete facts that then you can use to calculate your speeds.